I'm Dr. Luxman, Associate Professor in the Department of Computer Science and Engineering, Rohini College of Engineering and Technology. The subject I'm going to take is operating system. Subject code is CS8482. The topic I'm going to take is memory management in Linux. Core subject is to understand the basic concept of memory management in Linux operating. So what is memory management? Physical memory management deals with allocating and freeing pages, groups of pages and small blocks of memory. It has an additional mechanism for handling virtual memory mapped to the address space and so on. It has a zonal DMA, normal and high memory. Physical memory is less than 16 KB, 16 MB, greater than 860. So DMA and high memory will be having 16 to 8896. So managing physical memory. If a page allocator allocates and frees all physical pages, it can allocate ranges of physically contiguous pages on request. The allocator uses a buddy heap algorithm to keep track of available physical pages. So each allocatable memory region is paired with an adjacent partner. Whenever two allocated partner regions are both freed up, they are combined to form a larger region. If a small memory request cannot be satisfied allocating an existing small free region, then a larger free region is divided into parts to satisfy the request. Memory allocation in Linux occurs either statically or dynamically. It uses a slab allocator for kernel memory. Page cache is the virtual memory and also manages physical memory. Splitting of memory in a buddy heap. If the 16 KB is divided into 2 8 KB, 8 KB divided into 4 KB, up to and so on. The slab allocator in Linux will be having the kernel objects caches along with the slab. Slab is the physically contiguous pages. The kernel objects will be 3 KB objects and 7 KB objects. Intermediately will be having the caches that will be mapped onto the slab allocator. Virtual memory system contains the address space visible to each process. It creates pages of virtual memory on demand and manages the loading of those pages from disk or they are swapping back out to disk as required. The VM manager maintains two separate views of a process address space. A logical view describes the instructions concerning the layout of the address space. The address space consists of a set of non-overlapping regions that is distinct, each representing a contiguous page-aligned subset of the address space. The physical view of each address space which is stored in the hardware page tables for the process. Virtual memory regions are characterized by the backing store which describe from where the pages of a region come. Regions are usually backed by a file or by nothing. The region's reaction to writes. The kernel creates a new virtual address space when a process runs a new program with the execute system call. Upon creation of a new process by the system call, after executing a program, it will be having it will populate an address with the virtual memory region. The kernel copies the parent address VMA descriptors, then create a new set of page tables for the child. The parent's page tables are copied directly into child with the reference count of each page covered being incremented. After the fork, the parent and child share the same physical pages of memory address spaces. Swapping and paging. So the paging system can be divided into two sections, page out policy and paging mechanism. The page out policy algorithm decides which pages to write out to disk and when the paging mechanism actually carries out the transfer. It can page out to either swap device or normal devices. Bitmap is used to track of the blocks in swap space kept in physical memory. Allocator uses next fit algorithm to try to write contiguous runs. Kernel virtual memory uses contain two regions, a static area and the remainder of the reservation section. So it contains a page table services, references to every available physical page, so that there is a simple translation from physical to virtual address and running the kernel code. Swapping and kernel virtual memory, executing and loading user program. So whenever the user calls a program, what will happen? The registration of multiple loader routine allows the Linux to support ELF and A.out binary formats. So binary file pages are mapped into virtual memory only when a program tries to access a given page will a page fault result in that page being loaded into physical memory. An ELF format binary file consists of a header followed by several page aligned sections. So loader works by reading the header and mapping the sections of the file It is separate regions of virtual memory. Memory layout of ELF programs, kernel, virtual memory, stack, memory mapped region. So to have the program text, initialized data, uninitialized data, and runtime data. We'll be having the forbidden region and board point. Static and dynamic linking. A program whose necessary library functions are embedded directly in the program's executable binary file is statically linked to its libraries. The main advantage of static linkage is that every program generated must contain copies of exactly the same common system library function. Dynamic linking is more efficient in terms of both physical memory and disk space usage because it loads a system library into memory once. So the possible questions are: explain detail about memory management in Linux file system. Thank you. Thanks for listening.